In the previous class, we have studied rather, the Maxwell's right hand thumb rule. Maxwell's right hand thumb rule was like this, that imagine you are holding a straight current carrying conductor into your right hand in such a way that your thumb points the direction of current flow. Then your fingers encircling the conductor will give you the direction of magnetic field in such a way that the head of the arrow indicating the direction of magnetic field will lie at the tip of your finger, and the tail of the arrow will lie at the root of your finger. That was about Maxwell's right hand thumb rule. The statement was like this. Another way of stating the same law is this, that is called Maxwell's corkscrew rule. It is called Maxwell's corkscrew. C-O-R-K, corkscrew rule. The statement of this law goes like this, that earlier the screwdrivers used to be of this type, that this is the blade and that used to be the handle. So in this case, the corkscrew rule, Maxwell's corkscrew rule states that imagine you are driving in. Here driving in means you are tightening the screw, and driving out means you are opening. So he said that imagine you are driving in a screw in the direction of current flow. Suppose the current is flowing from top to bottom. Current is flowing from top to bottom, and then I want to drive in. So to drive in a screw, when the current is flowing from top to bottom, I will have to move my handle like this. So this is the direction of rotation of handle, and try to notice it. At this, if it was 9, then it became 10, and then it became 11 and 12. So I can say this is clockwise direction. So direction of magnetic field will be given by this. Once again, the complete statement I will read for you. Imagine you are driving in a screw in the direction of current flow. Then the direction of rotation of handle will give you the direction of magnetic field around that conductor. This is the conductor. Here the pen is indicating conductor. The current is flowing from top to bottom. This is the handle, and if current is moving in this direction, and I want to drive in the screw, then I will have to rotate my hand in this direction. So that will be clockwise direction. If I am driving in a screw in the direction of current flow again, and now this time current is flowing from bottom to top, then to drive in such a screw in this particular case, my hand will have to move like this. And so this is if 3, then that will become 2 and 1 and 12. So this is anti-clockwise. That was about corkscrew rule, which was another way of stating Maxwell's right hand thumb rule. Now I will come straight on to this, and this is a circular loop. So about a circular loop, what we need to study is how the magnetic field, the pattern of magnetic field, and to understand it this way, that if there is a very big circle, let me say if there is a this big circle, some small part of the circle can be considered to be straight. So to find out direction of magnetic field around this, we will again use the Maxwell's right hand thumb rule. And now this is positive terminal, this is current is flowing like this. So at point A, let us say this is point A, the current is moving in upward direction. So I will have to handle it like this. My thumb will point in upward direction, and the arrowhead must lie here. So this will be the direction of magnetic field. And same current when flows like this, it goes like this and it will come here. Now if you allow me, just see here, if my thumb is in the direction of current flow, and then my fingers are encircling the conductor like this, so this arrow will have to indicate like this. And two additional arrows I have put, that if you want to measure the strength of magnetic field at the center of the loop, then you will find that the nature of the magnetic field produced because of this segment of the loop, and the nature of the magnetic field produced because of this segment of the loop is same. It is in upward direction both. So we say this is additive nature, and the strength of magnetic field because of the additive nature being there at point A and B both will be more. So a circular loop is able to produce greater strength of magnetic field. Now we have to study again the same thing, the strength of magnetic field. Please do remember the strength of magnetic field is studied at the center of the loop in case of a circular loop. So number 1 point again it will be the strength of magnetic field will directly depend on the strength of electrical current. More current, stronger will be the magnetic field. Now second thing that we were to look for was that when we saw it, in case a straight current carrying conductor, when the needle was moved away, the magnetic compass was moved away, the amount of deflection was reduced. That means as the distance was increased, deflection decreased. And as the distance was decreased, deflection got increased. Similarly, in case of a circular loop, you can say the strength of magnetic field will be inversely proportional to radius of the loop. Rather than calling it distance, in being a circular loop, we can say radius. So it will be inversely proportional to the radius of the loop. And third thing that I want to tell you is the strength of magnetic field in this loop will also depend number of turns that we take to make this loop. If you take a single wire to make the loop, the strength will be less. If you take more wires to make the loop, then the strength will be more. So three things that we have seen regarding this. Number one is strength of magnetic field will depend directly on the strength of current. Number two, strength of current magnetic field will be inversely proportional to the radius of the loop. And third thing is strength of magnetic field will be directly proportional to the number of wires or turns that you take to make the loop. So this was all about circular loop. Now we will come on to the solenoid. The definition of solenoid goes here. If you see, even a very simple definition is sometimes is most widely misunderstood. People say so. कि insulated copper wire wound on a cylindrical plastic or cardboard form a solenoid. Insulated copper wire wound on a cylindrical plastic or cardboard form a solenoid. But this is again half the information. Solenoid, the word is from Greek, and this means channel. And channel means you have to say additionally like this, that length of the solenoid must be greater than the diameter. You cannot have this much of diameter and this much of length. Here the length is less and diameter is more. So to be very precise while defining solenoid, say like that. A solenoid is a insulated copper wire wound on a cylindrical plastic or cardboard in such a way that its length is greater than its diameter. Then this is rightly defined. So having defined this, now we will see further that on what factors strength of magnetic field produced by a solenoid depends. Number one, again it will be directly on the strength of current. And number two, it is number of turns. Most of the books again say just number of turns. But let me tell you, you don't have to stay there. You have to tell number of turns per unit length. See, the strength of will increase if the turns are close by to each other. Now, if in a distance of 2 centimeters distance, if I have 20 turns, and another case I have 1 centimeter but 15 turns. So you see, number of turns absolutely, if you see, it is more. Number of turns, if you see, it is less here. But these 20 turns are there within a length of 2 centimeter, and these 15 turns are there within a distance of 1 centimeter. So here you will find the turns are closer together. So strength will be more in this case. So please do say this. The strength of a magnetic field in a solenoid also depends on number of turns per unit length. And the third thing, its strength depends on is the nature of core material. Okay, core material, while defining, I said could be plastic or cardboard. If we want to make greater strength, the maximum strength will be there when soft iron is used as core material. Just in continuation, we will define another device that will be electromagnet. Electromagnet is a special type of solenoid where the core material cannot be other than soft iron. See, it is solenoid if you have plastic, it is solenoid if you have cardboard, but the solenoid, when core material is taken as soft iron, then thereafter it becomes electromagnet. So electromagnet is a special type solenoid where the core material is undoubtedly the soft iron. So now again for electromagnet, if you want to say the strength of magnetic field depends upon what? Undoubtedly it will depend on strength of current. Undoubtedly it will depend on the number of turns per unit length. But this time you cannot say nature of core material, because every electromagnet will have its core as soft iron. So the third point is the strength of electromagnet depends upon distance between the poles. If the distance between the poles is less, the strength will be more, and if the distance between the poles is more, strength will be less. In next class, rest of the